Hello everyone, my name is Valeria AVILÉS and today I will present the modeling and control of HEXACOPTER by sliding modes based on backstepping with adaptive parameterization, which was performed by the Kiev Research Group of Militar Nueva Granada University from Colombia. The authors of this article are Dario Amaya, Olga Ramos, and who speak to them. This is the table of contents for today. First, I will make an introduction of the reason why it was decided to do this study, presenting in a very general way the problematic. Then I will talk about the methodology development to obtain the dynamic and kinematic equations that represent the system. Later, I will explain the design of the proposed controller with the simulation performance, and finally, I will show the obtained result with the conclusions. An unmanned air vehicle is an aircraft that can fly without any type of manual human control. The characteristics are they have a radio controller-driven component, but they are not limited only the instructions that they receive. They can perform activities or tasks autonomously, thanks to the level and hex sensor, gyroscope, and GPS that are incorporated in their electronics. And they are lightweight and highly resistant. Thanks to these characteristics, the UAVs have advantages such as low cost and consumption, high reliability, small size. They have the ability to fly stably in any direction and maintain a desired altitude, which means that these devices are an effective alternative to execute the works in different areas like shows, surveillance, force fire control, monitoring, construction, military mission, and target tracking. Additionally, these aircraft are composed of a mechanical components, which are structure, that is a part where the rest of the components are mounted, propellers, motors, and by electrical components as electronic control that is responsible to control the speed and direction of the drone, battery, remote control, and a controller board that this function is to achieve stable in flight by transferring information to the electronic control. Based on the above mentioned, these devices are used for many applications. Hence, they are exposed to environments with geographical complexity, where different situations arise in which they are subject to disturbances, such as those provided by the weather, for example. In addition, they also have several uncertainties present in actuators, sensors, nonlinear parameters, variations, and measurement. Errors that are tried to be reduced by their own components and that are generally not considered in the remodeling of the device. Properties that, combined with the nonlinear couple and complex dynamics of the UAV, makes the control task one of the most demanding within the whole design. It is for this reason that in these works, it was proposed to develop an adaptive control strategy that can admit these uncertain parameters. In the picture on the screen, we can see the schematic representation of the study drone, where the rotation that can be performed in wall pitch and yaw are indicated. Already with that established, the equations that describe the system were obtained. From this, different methodologies were proposed. The methodology for kinematic model consists of 3 steps, which are obtain the total rotation matrix, calculating the angular velocities of the inertial system, and obtain the vector of angular velocities. In relation to the dynamic model, for this one, these considerations were taken into account. These initial considerations. As for the methodology, this is composed of 5 steps, which are obtain the thrust for at sea, do the force summation and apply the Newton-Euler method, which says that the mass times acceleration is equal to the sum of the forces, obtain the acceleration in the initial frame, calculating the matrix of total moments of inertia, and finally establish and solve the dynamic equation that govern the hexacopter rotation. From this process, the following equations were obtained, which represent the dynamic of the system for both orientation and translation. This can also be represented in a matrix form, as they even display on the screen. The proposed controller is one by sliding modes based on backstepping technique. This controller combines the design of a state feedback controller with a Lyapunov function to solve for system stability, and search create a feedback control that stabilizes the system at its origin, independent of the number of possible disturbances. In order to comply with the objectives, the controller divides the state space from a sliding surface in such a way that any point can be related to the surface, Usually upon a function to provide convergence or stability criteria, and in each iteration, it recalculates the system of physical parameters. For the design of the controller, a methodology was also proposed, which is composed of 3 steps. The first step consists of defining the sliding surface. The second consists of guaranteeing the stability of the system thoroughly upon a function, which in turn must comply with 3 stability rules. This proposed function already complies with the 2 initial ones. As for the third, this indicates that the derivative totally upon a function must be greater than 0. For this, a control loop is proposed that is composed of an adaptive part that comes from the state dynamics of the system, and a robust part that is responsible for ensuring that the third rule is met. As for the third and last step, it consists of finding adaptive parameters. This slide shows an example of how the design will be done for one of the variables role. For this, the first thing to do is to rewrite the dynamic equation so that the physical parameters are grouped together like this. Then, the sliding surface is defined with the respective error. The control loop is proposed, and finally, with the same value of the loop, the uncertainty parameters are estimated that also depend on the variation of the sliding surface. This same process should be performed for each of the variables. That is, the control system will be the one present in this diagram. And the simulation was done in the MATLAB software for which the other 45 function was used to solve system of equations. In this case, the system of equations is given by this flowchart, where all the steps are made for each of the variables. And these were the control gain used, which were found by tuning. These were the results obtained for the orientation variables, where all of them were set to 0 degrees. And here we can see how the uncertain parameters change according to HEXACOPTER dynamics. Here the results for the translation are shown. It can be seen how the system search for each of the reference until it reached it. For this, an ascending spiral trajectory was proposed, where the good performance of the controller is appreciated, as well as the uncertain parameters that are adapted and recalculated for each of the cases. Finally, the conclusions obtained were the hexacopter is a complex plan that requires a robust controller to operate as expected, such is the case of backstepping control that, from knowing the dynamic of the system, achieves the convergence of all states of a sliding surface, ensuring the stability of the same. The adaptive control generate good performance results for the tracking of variables and constant reference over time. This characteristic was evidenced by the control signals obtained for each of the cases, since these vary depending on the behavior of the input, allowing an adjustment of the physical parameters affected by the uncertainties which were cancelled without presenting great control efforts. The control strategy is robust because its stability is not affected by the uncertain parameters, providing great advantages by ensuring stability, robustness, and management of the desired dynamic property, which are generated with fast position changes of the UAV, or increasing the speed of response of the actuators. And finally, by tuning each of the control constants, it could be evidence how the constants K modify the signal of control variable and how the constant alpha affects the error signal, which is reflected in the system oscillation. The references are shown below. Thank you for your attention.
Thank you very much for your presentation.